Thanks very much for your introduction and the organizer for inviting me for multiple workshops. I guess you all are very eager to go to lunch, so.
Only me.
Okay, I am. So I will mostly talking about this material, zirconium tellurium 5, and then sharing some interesting results out of this. And then it's very interesting because it's a very confused material. And then what do we mean by confused material? If you Google search zirconium tellurium 5, or try to find papers out of this, then you'll find a bunch of different papers by saying different things. Some of them saying it's a strong topological insulator, some of them saying that it is a gapless direct metal, and some of them saying that it's a weak topological insulator. So what is zirconium tellurium 5? So actually, it is not a confused material. It is a critical material. It is a topological critical material that, in some sense, is really living close to this special critical point in this universal topological phase diagram where you have a tunable parameter control the bending inversion, changing from strong topological insulator to weak topological insulator, and then you have vertical axis control inversion symmetry breaking that drive the system into a wild metal as long as you are getting close to this topological critical point. And we think that zirconium tellurium 5 is really just living very close to this area, so therefore it gives rise to a lot of interesting property. For example, like I hope at the end of the talk I can convince you that you can actually use uniaxial strand to go through that critical point and then complete logical phase transition, going from strong to Dirac and then to weak topological installation. And then in the same time, just because it is very close to this topological critical point, so the bulk band structure is also very interesting because it is actually just a Dirac dispersion with a very small mass, and then which can tunable by this strand. And then this three-dimensional Dirac dispersion gives rise to basically a three-dimensional analog of graphene, and then we apply very strong field and then go to very low carrier density. You can see various very interesting behavior in an ultra quantum limit, and then I'm going to talk about some of that. We rotate the magnetic field as function of angle. So, of course, I'm not actually the one who do the experiment. This is really driven by my student, Josh March, sitting here. He's one of my first students in my group. And then we also got theory supports from Anton and Dri from University of Washington, and then some density functional calculations from my friend Chen Chen, University of Alabama, and then also acknowledge all this funding agency for support of this research. So I will start with the strand-tuned topological phase transition. Let's first give a quick overview of what this material is. So it is actually a van der Waals material, so just like the NOS2 and WT2 that I was talking about earlier. And but this material is, I would rather describe it as a quasi 1D than quasi 2D because the basic unit is some zirconium tellurium chain going along the A direction, and then they connected together along the C direction and forming a plane. And then one end this layer is bounded through the van der Waals force along the B direction. Now, this material has a long history. It has been studied as early as 1980s, and people initially thought, in the context of quasi 1D material, it could form charge density wave. But there's really, and then it also really shows some very strange R versus T curve that somewhat look like a charge density wave. But eventually, there's really no very strong evidence of any phase transition in this material. And it got more attention recently because there's this paper by Shidai et al. That if you make it to the monolayer, and then it is actually a quantum spin hole insulator with a gap as large as 100 millielectron volts. Although it's not yet been proven, no monolayer device has actually been made, but actually a more interesting thing was being found in the three-dimensional version of this, that is stacking this quantum spin hole insulator to a three-dimensional ball crystal. So what happens when you stack some quantum spin hole insulator to a 3D? All speakers discussed yesterday that one possibility is forming a weak topological insulator, right? You basically transforming this edge states into 2D layers to a 2D surface state on the side surface. But another possibility is that you can have extra fan inversion and then eventually forming a strong topological insulator with surface states of all crystal surfaces. So they also did these calculations, but interestingly, they found out that they cannot determine whether it is a strong topological insulator or weak topological insulator. When they are using the experimental lattice parameter, they get a result of strong TI, and then when they're using a theoretical relaxed lattice parameter, they get a big TI. So that really puts this materials in this critical point phase diagram. This you can probably easily control it going from strong to weak topologically by some right tuning parameter. And then likely this can be controlled by the lattice constant. Now, of course, people immediately look into this possibility and then doing some DFT calculation and see how the band structure and how this topological phase evolve as a function of lattice constant. So this is a work that is reported in this paper that they calculated how the band structure evolved as a function of isotropic expansion and contraction. And what they found is that the ground state is a strong topological insulator, but you have to applying a expansion, right? Your lattice constant has to have a positive strength, about 2%, in order to undergo a topological phase transition from strong TI to weak TI. So that means that you have to apply a negative pressure, and then you have to apply 2.7% negative pressure. And no one knows how to apply negative pressure, right? And then 2.7% change of lattice constant is also a huge change of lattice constant. So instead, we took a different approach. We applied uniaxial strain. So using this device was first being introduced by Cliff Hicks from the Indian McKinsey groups back then. You can actually apply a strain up to 1 to 2% by combining this 3 piezo stack, and then which can individually control the motions of these 2 sample holders. And then if you mount a crystal across this gap between these 2 sample holders, then you can move this. You can control the size of gap and applying very large uniaxial strain in a very continuous, in-situ tuning fashion. Now, when you're applying strain, you're actually applying stress, and the stress is the force, and the strain is the response of the material. So when you're applying uniaxial stress, you'll, for example, you'll stretch the material along this way, but you'll also shrink the materials along the other direction. And that amount of ratio between of the strain between these two different directions, the ratio is called Poisson ratio. And for this particular material, the Poisson ratio is 4, meaning that when you strain this material, let's say by 1%, then it will shrink by 0.25% along the other direction. So that means that you have to calculate the band structure not as a function of uniform expansion or contraction, but you have to kind of track out this 2-dimensional plot as a function of strain along the A lattice constant direction and the C lattice constant direction, both are in-plane direction, and then finding out what your trajectory are doing on this map of band gap versus strain along A and C and lattice constant. And what you can see is that the band gap actually has a very anisotropic response to the change of lattice constant. So the black corresponding to 0 gap, and then the white corresponding to the maximum gap. So in fact, you can see a valley corresponding to the 0 gap state, or the topological phase boundary, going diagonal across this map. So that means that you really want to contract the expand the A lattice constant. For example, if you're starting from this side, and then contract the C lattice constant to very efficiently, and then go across this topological phase transition. In contrast, what the previous paper proposed is doing an isotropic expansion, which means you're increasing A and C in the same time. So that is going parallel along this valley. So that's why they need about 2 or 3% in order to actually cross this phase boundary, because they're going along the wrong direction. Instead, this anisotropic strain induced by uniaxial strain is the right direction that going very efficiently to this topological phase transition. And this gray arrow corresponding to the actual Poisson ratio of this material and then the kind of strain we produce. And then you can sample the individual point and then calculate the band structure, and then indeed it looks like a massive Dirac dispersion and then a gapless Dirac semi-metal phase exactly at the phase boundary, and then an inverted band on the other side of the phase boundary. Okay, so now it looks like this is the right way to tune the material, but how do we actually see that there's a gap closing and reopening? So in reality, all this material is lightly doped, right? So if we can actually make the materials within the gap, then you probably may see an insulator to metal and then back to insulator transition. But in reality, what happens is that you always have some finite carrier density, and then it's just inevitable for this kind of small gap semiconductor. So the Fermi energy is probably about 5 to 10 millielectrons volts away from the band edge. And what you're probing is the transport of property of the quasi-particle cutting at this band energy. Now, when you modify the gap, so you're also changing the dispersion of this band. So therefore, your Fermi velocity and everything will change as a function of the gap. So you'll expect your resistance change as a function of the mass of this massive Dirac fermion. And then because the resistance shouldn't depend on the sign of the mass, so the lowest order expansion should be the square of the mass. And then since the delta rho over rho, which is what we actually measure, is a dimensionless quantity, and then the only way to normalize this mass is Fermi energy. So we expect your delta rho over rho to be roughly equals to mass divided by the Fermi energy squared. And this is exactly what we observe. We see that resistance following projective dependence as a function of strength. And this is actually quite striking because for most semiconductor, when you're applying strength, you will usually see linear response. It's very unusual to see such a non-monotonic, strong response. And then if you fit this quadratic dependence, you can get a coefficient, and that coefficient directly tell you what the Fermi energy is, provided that you actually know the deformation potential, that is how much mass you change as a function of strength. We use that deformation potential we obtain from the DFT calculation, and we extract the Fermi energy, and it agrees very well with the, let's say, the Chi density we measure from Hall coefficient or the Fermi energy people measured in practice. The other consequence of when you're sitting at this massive Dirac semi-metal is that you may see this chiral anomaly, and then I guess I don't need to make the introduction of chiral anomaly since it has been introduced many times. And then just want to point out that there's some ambiguity associated with that because the current jetting may result in similar kind of phenomenology, the negative longitudinal magnetic resistance. So you need to do a very careful contact geometry to make sure that you're not measuring current jetting, but actually a chiral anomaly. But another way to kind of verify this is that if you can actually control the topological phase of your materials and then tune in and then switching the, let's say, switching the from one topological phase to the other, and then see how this chiral anomaly or the quantity you measure change as a function of control parameter, that you can also verify that this is actually the physics what you're trying to probe. So for the Zirconium tellurium 5, because this is so close to the massless Dirac semi-metal phase, then people actually have observed a chiral anomaly. This is actually one of the first material people have seen the negative longitudinal magnetic resistance. And the way it works is that even though it is slightly gapped, but as long as your Fermi energy is far away from the Dirac point, then it doesn't really care whether you have a small gap open the Dirac point. But if your gap is larger and larger, eventually it will affect your chiral anomaly, and then you should see a decrease of your chiral anomaly. And this is indeed what we saw. Now we align the material so that you measure the longitudinal negative magnetic resistance and then apply the strain at the same time. The gray curve corresponding to the situation where your zero field resistance is sitting at a minimum, which is supposedly to be at this gapless Dirac semi-metal phase. And then indeed, this gray curve gives you the largest longitudinal negative magnetic resistance. And then when you straining away, either going to the strong TI phase, the blue curve, you gradually suppress this longitudinal negative magnetic resistance, or you go to the other side, you also suppress this longitudinal negative magnetic resistance. And then to be more quantitative, we also plot the magnetic conductance. So now it is positive, fit the B-squared dependence of that, because the B-squared coefficient directly gives you this chirality relaxation rate, and then this chirality relaxation time should diverge as you gap close. And then indeed, this chirality relaxation time showing a divergent dependence as you approaching the minimum, strain minimum, or the critical point. Okay. So this is the strain tuned topological insulator. Now I'm going to switch to this magic angle effect that we observe by applying magnetic field and rotate the changing angle. So so we want to make the material to a very low carrier density to actually probe the physics very close to the Dirac point. Now this material is actually very sensitive to growth condition to chemistry stoichiometry. For example, like in this paper, people show that if you're using the CDT method and you you will have a crystal, something like this blue curve, resistant as a function of temperature. You show a peak at around 150 Kelvin, and that's actually corresponding to a transition going from P-type to N-type. Now, instead, if you use a flux growth, and you can actually grow a crystal where you never see a peak, or you can say that the peak is almost at a zero temperature, the material is always P-type. So, and then it turns out that if CVT sample has like a 10 or 5% Hofstadter matrix, so it's heavily doped with a carrier density about 10 to the 17, whereas the red curve gives you the carrier density about 10 to the 15. So, okay. So, right. So we kind of doing all kinds of crystal growth, and then reduce the carrier density by optimizing the crystal growth recipe. For example, like arc melting the zirconium, and then carefully cleaning the crucibles. So we're able to get the carrier density down to about below the 10 to the 15, and then with the mobility about a medium. Now, you can also really reduce the quantum limit, which is the magnetic field that drive all electrons into Landau level, to an extremely small field. So, for example, like for this green crystals, you can see quantum oscillations with 1/B oscillations, and with a periodicity about 1 Tesla. For the blue crystals, where you push the RVST peak down to 20 Kelvin, then the quantum oscillation has an oscillation frequency about 0.5 Tesla. So, and then for this black crystal, you're actually no longer seeing quantum oscillation. You probably reach the quantum limit as low as probably 0.1 Tesla, and then you begin to some very weird log B oscillations in the ultra quantum limit. So this is something very interesting, but I won't discuss more on this talk. Instead, I'll focusing on this angle dependent. So what happens when you rotate the angle? So if you go to higher temperature and a smaller field, what you see is that you'll see something quite conventional. You see a threefold oscillations, larger magnetic resistance when field is out of plane, lower magnetic resistance when field is in plane. And by the way, it's always perpendicular current, so there's no issue of the run-through force and angle. It's always transfer magnetic resistance, just changing its relative direction to the crystallographic axis. Now, this twofold oscillation can be easily understood as that you have higher mobility in plane and lower mobility out of plane. So you get this larger magnetic resistance when the field is out of plane. So this is low field in high temperature. However, if you go to low temperature with a field much beyond the quantum limit, then you begin to see some very distinct peaks in the angle dependence on magnetic resistance. You see this very sharp feature, sharp dip at this thing, 45 degrees, 62 degrees. And then you, and it's really interesting because you shouldn't expect any feature as a function of angle once you go into quantum limit. And then there's no more Shimnikov House oscillations, and then you're not seeing any feature in the Fermi surface. All the electron is already squeezed into the one Landau level. How, there's no extra factor to give you the angle dependence. And then indeed, this is definitely not quantum oscillation, because if you go to higher field, and then this angle doesn't change as a function of field. It's always staying in the same angles at any given field. So, and what are these angles? These angles are actually corresponding to the crystal lattice, real space crystal lattice vector. So the first angle, 43.38 degrees, corresponding to 0.11 of your lattice vector. The second angle corresponding to the 0.12 of your lattice vectors. So they are corresponding to real space lattice vector. And convince you, we also plot the RD theta and then plot it against B over C lattice constant multiplying tangent theta. If this is really pointing to that vector, then these angles you should see it at the integer values of this. You should see this feature appears at the integer value of this quantity, and then indeed you can see that 0, 1, 2 all appear in the integer value. So this is really strange, right? You have electrons just occupying probably 1% or 0.1% of your Brillouin zone. There's no way you can detect that the boundary of your Brillouin zone to know where your lattice content is. However, when it goes very high magnetic field, somehow it knows this underlying real space lattice, right? So this really kind of reminds you of another situation, which is the Hofstadter Butterfly people have observed in the two-dimensional system, which is the graphene on chrome nitride superlattice. So here, there's also an interesting interplay between magnetic field and underlying lattice, and somehow the electron in the magnetic field can actually know the underlying lattice constants. And then there's some special condition occurs, which is also the commensurate fielding condition. That is when the magnetic flux going through the unit cell divided by flux quanta is corresponding to a commensurate ratio, P over QP, and Q are integer. Then corresponding to this straight vertical black lines in this energy versus magnetic field diagram. So those corresponding to the situation where you no longer have this fractal state, but rather you have a continuous band, because in this commensurate ratio, you can always construct a supercell where you have one flux quantum per supercell, and then therefore effectively you're not applying any magnetic field, so you can form continuous band. And the effect of that has been observed by the Andre Gein screw, where as a function of magnetic field, they see these oscillations in the conductance and then whole conductivity. In the conductance, they see a peak in the conductance, and then in the whole, they see this resonant dispersion-like effect as a function of magnetic field. And this is independent of doping, right? So this is carrier density versus magnetic field, and then this oscillation corresponding to this vertical background. This is independent of doping. So this is not quantum oscillation, because quantum oscillation creates this band diagram. But here, this is independent. It's only related to the commensurate fielding of magnetic flux to the unit cell. So this really doesn't matter whether your Fermi energy is. Now, so how does this have anything to do with the three-dimensional system? So in fact, in 2000, there's a paper by Hoshino et al. That they calculate the situation of a three-dimensional Hofstadter butterfly, where you have a highly anisotropic dispersion. So this kind of fits into our system, where you have x direction hopping is much larger than y direction hopping, which is much larger than z direction hopping. And then if in the right condition, we will apply large non-magnetic field, and then as a function angle, then you can reproduce the whole Hofstadter butterfly spectrum as a function angle. And the condition where you see all this dispersive band is precisely the condition where you see where your field pointing to this commensurate angle. So you also have this b sine theta multiplying a over b, a b lattice constant. So basically, the flux going through the this unit cell and the flux going to that unit cell, whenever the ratio corresponding to a commensurate number, you'll see this line, and then that corresponding exactly to our the angle we observed. So if we compare this results from the 2D case, then we see a dip in the resistance that corresponding to a peak in the conductance, and then in the Hall effect, it's less clear, but you also see something similar in the Hall channel as well. Okay, so I think this is the end of my talk. In summary, we see this strange topological phase transition. We also see this very strange matching angle effects in the ultra-convoluted conductor. Thank you for attention.
Thank you. Question? No.
Yeah, very interesting. On the first part for the zirconium pentatelluride, as you said, it's a van der Waals bond material that's very soft. So why does it not glide when you strain it?
To cover, you sandwich the. So when you mount the materials, you basically applying strength both top and below. So you basically have epoxy cover the whole crystals.
That's right. But so when you do these experiments, they're perfectly reproducible in that sense.
Yes, yeah.
There's no hysteresis.
Swing back and forth, and then when you break the crystal, you'll see a crazy effect, and then unproducible hysteresis.
And maybe a second question, in terms of your interpretation then of the band gap closing, is there also the role of the symmetry breaking strain versus the isovolume strain? Does that matter?
So this is actually not a symmetry breaking strain, because the crystal is rhombic. So when we apply this anisotropic strain, it is still a A1G or no.
I see.
So that's why this this nonlinear elastic resistance is very striking. Because, you shouldn't expect any nonlinear response.
Okay, I missed that. Okay, cool.
So later on, you showed that you continue your samples to the quantum limit at very low fields. So this means that you must be very close to the charge neutrality point.
That's right.
That's right.
Yeah.
So couldn't you then use these same samples and do the strain experiment and just see matter-insulated transition?
Oh, this is the sample I show here is the same sample the similar sample. Right. So if you notice, as a function length here, we also didn't see quantum oscillations. That's because the quantum limit is too low. Right. So yeah, we didn't. What we saw is this whole strain tuning work is really focusing on very low credits. We're working on samples that you can see quantum oscillations and try to see how quantum oscillation change as a function of strength. But the problem is that when you go to more doped sample, which is usually n-type, it becomes more complicated because if you notice when you go to n-type, then there's this other indirect gap here, and then you kind of introduce the second pocket, and then it's less clean as a function of strength. And then if you're just focusing on the whole dope side, then you see a very clean Dirac fermion.
Maybe just follow up. So can this strain story somehow explain the previous experiments?
You mean why all this inconsistent? I think so, yeah. And there's more recent work, people see this potentially topological phase transition as a function of temperature just by thermal expansion. And then, I have a...
How much thermal expansion is it?
Thermal expansion is usually of order 0.1%. It probably differ for different lattice constant. And then one of the experiments we did was we glue the samples on this piezo stack, which has very anisotropic strength. So if you glue the crystal this way and glue the crystal that way, you'll expect very different thermal contraction, thermal expansion. And then it turns out that the crystal growing this way and the crystal gluing this way are seeing the different topological phase, based on our interpretation of strain-induced topological phase transition. So very likely, so different people do different measurements, glue in different substrate and prepare in a different way. And the crystal itself is probably vary from batch to batch, so you can get mixed results.
Can you ever get into the vial phase?
Not for all this bulk crystal measurements because you need to break conversion symmetry. And then we're trying some thin plate, which potentially apply vertical electric field.
Okay, so you couldn't do like inversion breaking strain, that would just ruin it?
Strain generally doesn't break it. You can.
You need something else.
You probably usually need inversion symmetry is already broken and applying strength, and you can probably strengthen the polar vector from that. But we're thinking about looking for some inversion symmetry breaking material and see if we can use some strength to go across this topological phase network. Like not around here, but maybe around here. That would be interesting too.
I noticed there's some experiment report that say this material has a huge G factor, like 10, 20.
That's right.
Yeah, do you think apply, like suppose in that strength case you have a really small pocket, right? You apply magnetic field, it's big enough to split the bands?
I mean, seeing a gigantic anomalous Hall effect or something like that, creating a magnetic well center top. I think it's possible. There's a paper by Wen-Ong. He claimed that he sees some anomalous Hall effect, and his interpretation is exactly my splitting. I can discuss with you more about this. I think we also get a lot of results on this, but we're trying to understand.
I see.
Maybe one last, somewhat related question. So you know that there have been these reports on these 3D quantum Hall things in zirconium pentatelluride. Have you ever seen something like this in your experiments?
We see something close.
Okay.
We see something close. We're trying very hard to reproduce it. I mean, somehow they don't have the lowest carrier density sample, but they definitely have the highest mobility sample.
Yeah.
So you need a extremely clean, simple, extremely long free patches.
That's right.
Yeah.
I have a question. In this strand one, do you have a way to estimate at a zero strand how large the gap is? Although your fragmented don't cross it.
I mean, if we
The
don't
band gap,
apply any
yeah.
strand, then where does it land?
Yeah. Do you have some way to know
Yes,
the gap?
right. So we try to do that, and then the insurance is failed because for some the way we do that is that you can actually measure the crystal without applying any strand. Measuring R versus T, for example, and then when you're putting on the device, then because the device has all kinds of thermal contraction, so you'll just naturally strand the crystal. But because now we can tune the strand, we can tune it back to the zero strand state by referring to the zero strand resistance versus temperature measurement. You can do that all the way down to 60 Kelvin. But somehow below 60 Kelvin, we always lost track. Yeah. Okay. The only thing I can say is that we can give an upper bound of the gap, maybe around 20 millivolts.
It's an upper bound.
Yeah, that's the upper bound that numbers.
Thanks. Do you have more questions? If not, I suppose it's a real last talk, right?
Yeah. Thanks very much.